Hi everyone, my name is Shuyi Guo and I am very glad to present our work, Detecting Toll Bridge from Sampled Traffic in Backbone Networks. We all know that toll is designed for free speech anti-censorship, but there are also cybercrimes. Illegal drugs and personal information sold by criminals can cause harm to society, so criminals in the dark web need to be tracked. Before tracking criminals, we first need to detect toll traffic in backbone networks. To enhance anonymity, obfuscation protocol and bridge are used in toll, which increases the difficulty of detecting toll traffic. Toll network is a part of backbone networks and traffic sampling is widely used in backbone networks. So we need to learn how to detect the toll bridge from sampled traffic in backbone networks. To achieve the purpose, we put forward the following work. We extract 40 features that are still available in the post-sampling traffic that can be used for toll bridge detection. We design a new structure called nested count bloom filter to store the statistics of the sampled packets in the backbone network. We mix the toll traffic with real backbone network traffic in different ratios in our experiments to validate the usability of our method. Now I will introduce the background. The detection of toll traffic is based on the traffic captured from the client side. It can be seen from the basic structure that toll traffic can be identified by TLS fingerprints. But when the bridges are used, traffic is pre-processed by the obfuscation protocol. Machine learning is a better choice for detection. Because toll network is a part of backbone networks, the detection of toll bridge facilitates the backbone network management. Traffic sampling is widely used in SDN measurement and other fields, and the central limit theorem can prove that the samples can represent the overall traffic. After traffic sampling, there are still many packets. To efficiently store the statistics of these packets, we design a new structure based on count bloom filter. CBF is an improvement of bloom filter, both an efficient storage structure. In the initial state, BF is an n-bit array and each bit is set to 0. When inserting elements into BF, the element is processed by k-hash functions, then mapped to k different bits and sets these bits to 1. When performing a query, the queried element will be processed by hash functions. If the mapped bits are all set to 1, this element has been recorded in BF. As we can see in the figure, this bit isn't set to 1, and this means that the element Y hasn't been recorded in the BF. The difference between BF and the CBF is that CBF expands every bit into a counting cell, then it can record one type of statistics. Because traffic packets have many statistics, CBF cannot be used for storing packet statistics. If multiple CBFs are used for storing, then each CBF needs to perform hash functions, and this will increase the memory and time consumption of the calculation. And the next part is the detection methodology. Based on the background information, we put forward our method to detect toll bridge. The methodology is divided into 3 parts. First, we build a machine learning model for detection. Then we sample the traffic in backbone networks and using the new structure to process the packets to get samples for detection. Finally, we put the samples into the model and get the bridge list. To build the machine learning model, we need to extract and select the features. The traffic dataset we use is collected by ourselves. The dataset includes normal traffic and toll traffic with bridges. We first extract 5 types of features based on complete traffic. Then we use random forest algorithm to evaluate the feature importance of these features. Considering that the traffic will be sampled, we need to select features that can still be used after sampling. At the same time, it is necessary to reduce the computational cost as much as possible. Finally, we get 14 features, and they are all proportional features. To calculate the value of the features, there are only 12 statistics need to be recorded, and we use the random forest algorithm in Python and the default settings to build the model. In the backbone network, traffic sampling is widely used, and there are 3 basic packet-based sampling techniques: systematic sampling, random and out-of-n sampling, and uniform probabilistic sampling. Compared with the other 2 sampling techniques, the systematic sampling technique consumes less time and memory. Therefore, we choose this sampling technique. After sampling, the packets need to be processed to get the value of the features. So we designed the NCBF structure to store the statistics of packets. NCBF expands each bit of BF to 1 counting block. Each counting block is 1 CBF. When a packet is inserted, it will be processed by hash functions and mapped to different counting blocks. Because each counting cell of CBF can add 1 for multiple times, the packet statistics can be stored in each counting cell. When the certain statistics, such as the amount of non-empty packets, reaches the threshold, the statistics in this CBF will be extracted to calculate the value of features. NCBF structure also has the same problem as BF. If too many data packets are inserted, there is a certain probability that the later data packets will be mapped to the wrong block, causing errors in the statistical data of the block. Before we insert the packet, we need to know that each packet has a quintuple, including source IP, destination IP, source port, destination port, and protocol. As we can see from the figure, packet X has been mapped into K blocks. When packet Y with different quintuples is inserted, it will also be mapped to K blocks. But we can see that in this block, a hash collision occurs. So when we deploy NCBF in backbone networks, we should allocate appropriate memory to reduce the probability of hash collision. Next, we conduct experiments and get the results. First, we need to discuss the parameters of NCBF to allocate appropriate memory to reduce the probability of hash collision. Considering the low ratio of toll traffic, NCBF should process the traffic for a long time to ensure that the statistics of sampled packets can reach the threshold. From the former slide, we know that the elements causing hash collision is the packets with different quintuples. There are many packets with the same quintuple. If the quintuples are different, the later inserted packet may cause hash collision and make the statistics of former packets wrong. The probability is called FPR in BF and can be calculated by this formula. Because 12 statistics can be used to calculate the value of the features, we set each counting block to 12 bytes, and the total memory can be calculated by this formula. Because NCBF should process the traffic for a long time, we not only need to consider the memory, but also need to consider the traffic duration. When the NCBF has processed the traffic for a long time, it should be cleared, otherwise the probability of hash collision increases. So we use this traffic dataset for calculation. It is a 15-minute backbone network traffic with different quintuples, and the traffic duration can be calculated by this formula. By changing the sampling ratio, NQB has different values shown in the table, but they all represent the 15-minute traffic. When we set the value of K2 for the value of FPR to 1, the 100s, by changing the value of M, we can get the result. From the table, we can know that when the sampling ratio is 16 to 1, we set the memory of the NCBF to about 10 GB. The NCBF can handle the backbone network traffic for 2 days. When the sampling ratio increases, NCBF of the same memory can process the traffic for a longer time. After adjusting the parameters of NCBF, we perform the experiment to prove the availability of the method. First, we collect the traffic, build a simulation backbone network traffic dataset, and then adjust the ratio of toll traffic. When collecting toll traffic, the bridges we used were applied via HTTPS and email, and we adjust the ratio by changing the number of toll traffic files. After changing the ratio, we used a random function to modify the time starting point of toll traffic and inserted each toll traffic file into the different time points in the public traffic file. Then we sample the mixed traffic and using NCBF to process. Finally, we put the detection samples obtained from NCBF into the random forest model to get the detection results. In the results, we first need to analyze the sampling results. Because of the low ratio of toll traffic, there may be few toll packets after sampling. The sampled packets will be processed by NCBF. Then we need to determine whether NCBF can calculate the value of features from the sampled packets. We define the packets with the same quintuple which reach the threshold as a record. What we need to analyze is the number of records after NCBF processing the sampled packets. And here is the result. The figure demonstrates that NCBF can process the sampled packet to obtain the records in large-scale traffic environments with low toll traffic ratios. Since the bridge addresses used in the experiment are in a unknown state, the precision recall and F1 score for toll bridge detection with different traffic ratios and sampling ratios can be calculated. Part of the results are shown in this table. From the table, it can be seen that as the ratio of toll traffic increases, the precision rate has increased significantly, and the recall rate has stabilized above 95%. High recall rate means that the number of the real bridges which identified as bridge accounts for a high proportion of the number of the real bridges, which means that the detection results are relatively complete and the real bridges are almost in the detection results. Therefore, when the detection is performed in the actual network, it is only necessary to perform a second identification based on the first detection result. And then we put forward the discussion. We compare our method with two other methods. The result shows that their methods are all use the complete traffic and don't consider the low ratio of toll traffic. Processing complete traffic consumes more resource. which makes their methods are unsuitable for backbone networks. But the research agent gets high precision rate. In the future work, we can adjust the machine learning model referred to their research. And the limitation of our research is also obvious. The toll traffic we used for validate was almost collected around July in 2020. If there are some changes in the obfuscation protocol, we need to reselect the features. Based on the features, the countermeasures can be put forward, such as adding padding in the information control part of the packets, shielding ultra-small data packets. Finally, we conclude our work. In our work, we put forward a method to detect toll bridge from sampled traffic in backbone networks, and the experimental results show that our method can get high recall rate and available when the ratio of toll traffic is very low and after traffic sampling. In the future work, we need to study how to design a secondary detection method, maintain the usability of the method when the obfuscation protocol update causes the old features to be unavailable. And here are our references. This is my presentation. Thank you for your listening.